Down to a minimum. There's a lot of people in the class, and we're going to be having some more people as well. All right. So what we're working on now is section 1.3, and section 1.3 is oops, sorry, wrong one. Okay, let's back up here. Okay, so we're on section 1.3, and 1.3 is the derivative. So last section, what we talked about was the slope of a line, all right? And we ended with the slope of the tangent line. So the way the course has progressed so far is we started talking about lines, and the reason we started talking about lines are because lines are easy. Lines have a constant slope, okay? That's a key point to remember from section 1.1. We talked about the equations of lines, and we talked about the slope of a line as the rate of change, okay? In section 1.2, we tried to just get an intuitive idea of what the slope of a curve would be, okay? So, for instance, if you're looking at a car accelerating, the rate that the car is gaining distance is increasing over time. Just not the distance is increasing, the rate that the car is gaining distance is increasing. So there's an acceleration there, okay? When you start plotting things like that, you don't have straight lines, okay? If you're looking at the example where we had the woman that was selling some sort of good, right? Every item she sold, she got $5. If she sold one box, she got an additional $5. If she sold two boxes, she got an additional $10. If she sold three boxes, she got an additional $15. Okay, that's a constant rate for every item sold. She just gets $5 more. Okay, an acceleration is if she gets $5 for the first box, and another $5 for the second box plus a 20% increase or some sort of bonus, right? That would be an example of an acceleration. It's not constant. The more she sells, she gets that base rate plus something extra, right? Okay, so that's an example of an acceleration. The problem, as we saw in section 1.2, if I just back up a second, when the rates are not constant, we don't wind up with straight lines. We wind up with things that have kind of funky shapes to them. And that's where we ended about talking, okay, we talked about approximating these points by lines, these rates by lines, and finding the slope of these lines. We call those tangent lines. And the slope of these tangent lines is what we're going to call the derivative, right? So we're going to look at how fast something is changing at a particular point in time or a particular place on the graph. For instance, if we look at, say, this graph, if we look at the change in thousands of dollars at the year 2000, this flat line represents that there's a zero rate of change over here, because a flat line has a zero rate of change. So we just kind of intuitively draw lines on this chart and see what would happen. Over here, between 1970 and 1982, if you look at this point over here, it has some positive rate of change that's approximated by the slope of this line. So section 1.2, we looked at just drawing lines on the graph and, just intuitive guess, and then say, okay, what's the slope of the line we just drew? All right. Now, in section 1.3, we're going to, given an equation, how to determine the slope of the equation, okay, or the graph. So the section outline for this is we're starting out first with the derivative. Before I continue, were there any confusions on the stuff from last time that I can answer? No? Okay. So what we're going to look at in this section is we're going to look at what the derivative is. And then we're going to learn how to take the derivative. And then we're going to look at slopes of tangent lines, which is another way of talking about the derivative. And then we're going to look at different notations for the derivatives. Okay? So that's the whole idea. The derivative is the slope of a curve. Okay? The derivative is the slope of a curve. All right? It tells you how fast the curve is changing at a point in time. So the definition for the derivative that we're going to use here is the slope formula for a function y equals f of x. And how we're going to denote the derivative of, so if we have some function f, and we're evaluating, this does not mean f times x, this means we have some function x, it could be whatever formula you would like it to be, and we're evaluating it at x. If x is 1, we're evaluating the formula at 1. If x is 2, we're evaluating the formula at 2. We'll do some examples of that. And we're going to denote the derivative of this function f by putting a little apostrophe between the f and the x. So this is going to be, we're going to say f prime of x, or the derivative of f of x. Okay? So if we have a function x, the function that will denote its derivative, we're just going to put a little apostrophe between the f and the x. Okay? It's just a notation so the person reading your work can say, okay, this person is communicating the idea of the derivative, right? So a lot of mathematics is just notation or syntax to communicate ideas to the reader, okay? So the whole idea here is this over here is denotating a function. If we put the apostrophe there, it means you're communicating to the reader that you're looking at the derivative of the function. All right, an example of this, and this is going to get into what's called the power rule that we're going to get into in 1 second. If we have the function f of x equals x cubed, and we want to know how fast the function is changing at a particular value of x, well, the formula that tells us how fast the function is changing is given by 3x squared. Okay, so the top one is the original function, which is f of x. When I put the apostrophe here, it means I'm telling the reader this is the new function that tells me how quickly the original function is changing. Let me just expound on this example real quick. So we have f of x equals x cubed. And I'm going to put on the overhead in 1 second. And we have f prime of x, or the derivative, is equal to 3x squared. Okay? And I'm going to put another column for x. All right, so let me just flip over to the document. Okay, so we have this up here, and it just tells me for a particular value of x. So if I put in x is equal to 0, and that means that, well, f of 0 is equal to 0 cubed, which is equal to 0. So it tells me the value of the function is 0, but how fast is the function changing when x is 0? Well, that's what the derivative tells me. So f prime of 0 just means I replace x by 0 is equal to 3 times 0 squared, right? Well, what if x is 1? Well, if x is 1, the value of the equation, or the function f of 1, is equal to 1 cubed, which is equal to 1. A measure of how fast the function is changing when x is 1 is given by this formula up here. So f prime of 1 is going to be equal to 3 times 1 squared, which is just 3. Okay, and if you start putting units on this thing, then it starts to make more sense. Like if x is time, say for instance if x were time and f of x and f was a measure of distance, then the rate would be distance over time. So this might be at time 1 you'd be moving 3 feet per second or something like that, right? When you've covered a distance of say 1 foot, you'd be moving, at 1 second you've covered one distance, you've covered say 1 foot, and the speed, your current speed at that time would be 3 feet per second, right? So we'll get more into that, so you can just ignore that for the second, and we'll talk more about it. But if you start putting units on it, it'll start making more sense, and say either in a physical sense, physicists use this stuff a lot. People who do finance Certain types of finance use this stuff a lot. Actually, a more complicated version, which is called stochastic calculus, but it's based on the same ideas, right? So it's when you start putting units, it starts to become more meaningful, or it'll make more sense. Okay. All right, so differentiation is the process of computing a derivative. So if you have a question on a quiz or a test or something that's asking you to do differentiation or take the derivative, you're going to compute what the derivative of a function is. Okay? For the example, it says, don't worry, we'll get to that. So I guess, don't worry, we'll get to that. And actually, I think the next slide. Okay. So this slide is very important, and for this class, this is going to cover a lot of the rules of differentiation for you. Where does derivative come from? We're going to get to that in the next section, section 1.4 and section 1.5. But for now, we just want to have an idea of what the derivative is. So what the derivative is, it's a formula that tells you how fast a curve is changing at a particular value of x. You give me x, you give me the formula. The derivative of that formula at that x will tell you how fast it's changing. So how fast it's changing depends on what your x is. If it's a straight line, it doesn't matter. It's constant. Okay? So this slide right here is really important because for most of the derivatives we'll do in this class, this slide will basically covers the gist of it. We'll pretty much cover most of the rules you need for taking the derivatives in this class. The next section we're going to talk about limits and then talk about where these formulas come from. But for now, the first one, if we have a line, the slope of the line is m. So if your function is a straight line, f of x equals mx plus b, then f prime of x is just the slope of the line. It's just m. So if your formula, your function is a straight line, the derivative of the line is just the slope. It's m. If the derivative of your line is a constant, it's a flat horizontal line, it's not going up or down, the derivative of that line is 0. If it's a horizontal line, it's not moving up or down, and we'll draw some pictures of these things, it's not changing, the rate of change is 0. So let's just take a look at that real quick. On here, just quickly. So if we have the case where we have f of x equals mx plus b, and just for the sake of working with some actual numbers, we'll say f of x equals 2x plus 1. Okay? So that means that if I draw this out, again, it means that's the y-intercept, right? So it's just where we start the line essentially. So it means when x is 0, the y value is 1, so this is the point 0, 1. Now, the slope is going to tell me that if I go from 0, if I go 1 unit to the right, okay, that I'm going to go 2 units up. Right? So if I go 1 unit to the right, I'll do this in a different color. If I start at this point, since my slope is 2, it means if I go 1 unit to the right, I go 2 units up. And this is going to be the point 1, 3. Okay? And I can just draw a straight line connecting those 2 points. And a constant line, it's just we just keep doing the same thing, 1 to the right, 2 up, 1 to the right, 2 up, 1 to the right, 2 up. And we have that constant rate of change, makes a nice staircase. So it gives us a straight line. Now, the slope, the rate of change, the derivative of a straight line here is m, or in this case is 2. Now, the other case was saying it's still a line, but it's important enough of a line just to do a separate example of it because it's very important. But if we have f of x is, say, equal to some constant k, right? Well, this is a line because we can write f of x is equal to 0x plus k, where k is the y-intercept and the slope is 0. Okay? But if you have a constant line, let's look at the example where, say, k is 3. So let's look at the example. Let me use a different marker, where we have f of x equals 3. Okay? That's our constant line, so if we want to plot that, this tells me that no matter what x is, the function value on the y-axis, or f of x, is 3. So I'm just going to come up to 3, and we're going to draw this. The slope of this line has to be 0. It doesn't go up or it doesn't go down, right? No matter what x is. So in the example, it's like if the lady goes into work and she's selling boxes and she has that $60 base rate. It's basically like her boss tells us, you're gonna get $60 whether you sell nothing or you sell a whole bunch of things. Okay? You're getting that $60, and that's it. Okay? That would be an example. So the slope is 0 there. And here you get $3, and it doesn't matter what you sell or you don't sell, anything like that. You're just getting the $3, or in the case of $60. So a flat line gives you that slope of 0. It doesn't go up or down. Now, if we go back to our slide, suppose we have the example of x squared. Well, the derivative of x squared is going to be 2x. Okay? We're bringing the 2 in front, and we're subtracting 1 from the exponent. We're going to generalize that. The derivative of x cubed, now notice x squared is not a straight line, so the derivative has an x term in it. So it depends how fast the function is changing depends on what value of x you're plugging into the function, right? Because the slope of the curve is given by the formula 2x. If we have the function f of x equals x cubed, again what we're doing is we're bringing the 3 in front, we're subtracting 1 from the exponent. And that formula, the slope of the curve at that point is given by 3x squared. And in general, whenever we have x raised to some number, we have what's called the power rule. And the power rule says if I have a function of the form x to the r, and this is probably going to be the most common formula used in this entire class, at least for the first half before we get to integration where you're just going backwards. Is the formula over here where we have f of x equals x to the r, and the derivative of that is given by f prime of x, however you like to say it. You bring the r in front, we're going to do some examples, and you subtract 1 from the exponent. So let's do some examples of that. And in the next section, we're going to actually get into where this comes from. We're going to talk about a little bit of that in this section. But let's just talk about where that comes from for a second. So let's do some examples. So if we have, say, a function f of x is equal to x cubed. So to take the derivative of this function, the power rule says, and it seems a little strange why we do this, but you'll see why in a little bit. We're going to take the number up here, and we're going to bring it in front. And we're going to subtract 1 from the exponent. So f prime of x, since we bring the 3 in front, we're going to have the 3 here, and it's going to be x raised to the 2 because we're subtracting 1 from the 3. If we have, say, let's do another example. If we have, say, f of x is equal to x to the 5th, what we're going to do here, and it doesn't matter if you're dealing with a fraction, a negative number, anything. It's the same process. We'll do a couple other types. You're going to bring the 5 in front, and you're going to subtract 1 from the exponent. So you're going to have f prime of x is equal to 5x to the fourth. All right? So if we do an example, say let's do something with a negative number. Say f of x is equal to x raised to the negative 1. Well, it's the same process. What we do to differentiate this is we take the number up top, which is a negative 1, we're going to bring it in front, and we're going to subtract 1 over here, and that's going to give us x prime of x. Well, we're bringing the negative 1 in front. We always bring the in front, so it would be negative 1 times x to the negative 2. Did someone have a question? So, which is just equal to negative x to the negative 2, and so forth. And we can use this to take derivatives of square roots too, which we're going to do in the next slide. For instance, because, say, the square root of x is the same as x to the 1/2, right? And we're going to do an example like this in a second, but let me just do one here. And this, so if we have f of x is equal to the square root of x, well, the square root of x, if you remember from your algebra, if you don't remember how to convert a root into an exponent, see me after class or make sure to stop by the math lab. You'll be doing a lot of that, so make sure you take care of it right away. Well, from algebra, this is equal to x to the 1/2. So f of x is really just equal to x to the 1/2. I'm looking at the square root of x. So f prime of x, what I'm going to do is I'm going to bring the 1/2 in front, and I'm going to subtract 1 from the exponent. So this is going to be equal to 1/2 times x. Well, 1/2 minus 1 is what? Negative 1/2. So if you're looking at the function, which is f of x equals the square root of x, this is equal to 1/2 x to the negative 1/2, which is equal to 1 over 2 times the square root of x. And that's just some algebraic manipulation. And again, if you haven't seen that or you're uncomfortable, come see me. Stop by the Math Learning Center or even like the online sessions that they're having, and we're going to get some more info on that tomorrow also. But the general idea, if it's written as an x raised to an exponent, bring the exponent in front, subtract 1 from the exponent. If it's not x raised to an exponent, then at this point what you'll probably have to do is rewrite it as something raised to an exponent. Okay? So that's what we're doing here. We're going to find the derivative of f of x is equal to 1 over the 7th root of x. So I'm going to do it on paper, and then I'm going to go through it on the slide. And let's see, where'd it go? Here it is. So we're going to take the derivative. So what we're doing is we have the function f of x is equal to 1 over the 7th root of x. Now, I don't know how to take the derivative of the 7th root of x, at least not written like that. So what I'm going to do is I'm going to write this as 1 over x raised to the 1 divided by 7. And the reason I do that is because the power of x is 1 and the root is 7. So I put the power, it's the same as writing x raised to the power divided by the root. All right, and I'll say that again, but if not, see me after class or see a tutor or someone. But if you're taking, say, some root of x, and I will rewrite it as an exponent, I rewrite it as x raised to the power of x, which in this case is a 1 because there's nothing there, so I can either leave the 1 out or write it. So it's the power of x divided by the root you're taking. So here x is raised to the first power, or you can just, if you don't see anything on x, it just means there's a 1 there. We just don't always bother writing it. So x raised to the 7th root of x raised to the 1 is x raised to the first power divided by 7. Now what we do is, since this is on the bottom, we can bring it up top and change the sign. So this is the same as x is raised to the negative 1/7, right? So now we know how to take the derivative of this, so we can proceed. So we know f of x is equal to x raised to the negative 1 divided by 7. And we're going to proceed as before. So the process is fairly simple. A lot of times where students will get challenged with this is just recalling some of the algebra. They might know how to take the derivative of this, but a lot of times rewriting it in a form where you can use the power rule is where someone just recalling some of like the algebra rules and stuff like that. So if you're a little rusty on that, make sure to get help with that right away. But what we're going to do is we're going to bring this term in front. We're going to subtract 1. So this is going to be f prime of x is going to be equal to negative 1 over 7 times x to the negative 1 over 7 minus 1. And negative 1 is 7 over 7, which is going to be equal to negative 1 over 7 times x to the negative 8 over 7. Okay? Very good. Whoever said that, it's good. And the reason that's true is negative 1 over 7 minus 1. Well, 1 is just 7 over 7, so this is equal to negative 1 over 7 minus 7 divided by 7. Because 7 divided by 7 is 1. And negative 1, since the bases are the same, you can just subtract the numerators. Negative 1 minus 7 is just, if you're $1 in debt and you go out and spend another $7, that gives you minus 8, so it's negative 8 over 7, and which is what we have here. Negative 1 over 7 minus 1 is negative 8 over 7. Okay, so let's just run through what they're doing here. Okay, and let's see. Okay. So again, what they're doing is they're just rewriting it first like I did. The 7th root of 7 is x to the 1 over 7. Bring it up top by putting a negative on the exponent. And now we can just use our power rule. We bring the negative 1 over 7 in front, subtract 1 from the exponent, and they get the same answer as we do. All right. So here's another problem. Here what we want to do is we want to find the slope so we have this curve, and if you want to use function notation, say f of x equals x to the 5th, or if you just want to use the simpler notation used a lot in algebra, just because it's a lot less to write sometimes, you can say y equals x to the 5th. All right, and we want to know how fast is this curve changing when x equals negative 2. So let's do that on paper, and then we'll see how they solve it, which is going to be the same thing. So we have the curve, and the two usual notations we use for functions, the most common will be f of x, functional notation, or we might just use y to represent the function. Okay. So here, instead of f of x, we're just going to say y is equal to x to the 5th. So the derivative, y prime, is going to be equal to what? Can someone tell me? Very good. Y is equal to 5x to the 4th. And we want to know how fast is the curve changing when x equals negative 2. So we want to know how fast the curve is changing when x is equal to negative 2. Well, to do that, we just plug that into our rate formula, or our derivative formula, or our slope formula, however you want to say it. So we're going to say y prime at negative 2, just evaluating at negative 2, is equal to 5 times negative 2 raised to the 4th. I'm just replacing the x by negative 2. I'm evaluating this formula that tells me how fast the curve is going for a particular value of x by swapping in negative 2 for the x, which is going to be equal to 5 times 16, because 2 times 2 is 4 times 2 is 8, which is 16. And that becomes 50 plus 30 is 80. Right? 5 times 10 is 50, 5 times 6 is 30, add the 2, you get 80. Right? Okay, so when x is equal to negative 2, The function is changing as a rate of 80. 80 what? Well, it could be feet per second, dollars per hour, something. All right? This tells you how fast the curve is changing at a particular value of x. And what is the value of the function when x is -2? Well, the value of the function, if we don't want to know how fast it's changing, we just want to know what is the value of the function when x equals -2. We just say y of -2 is going to be equal to just -2 raised to the fifth. Well, -2 raised to the fifth, well, 2 raised to the fourth is 16. 16 times -2 is going to be -32. Okay. So when the value of the function is -32, the function itself is changing at a rate of 80 somethings. Okay. When we start sticking units on it, like doing physics problems or maybe a problem from finance or anything in that area, we'll have units and it'll be changing like boxes per hour, dollars per hour, feet per second. So it'll be changing at some sort of rate that you're familiar with. Okay? So let's see how they address it. So we want to find out, well, y is equal to x to the fifth. We want to evaluate it when x equals -2. How fast is it changing? Well, we use our power rule, f of x equals x to the fifth. The derivative, like you said, is 5x to the fourth. And, well, we just plug in -2 to figure out, that's our formula for how fast it's moving for a given value of x, so we plug in -2. And it's moving at a value of 80, maybe 80 feet per second, something like that, some rate of change. All right. Now we're going to talk about finding the equation of the tangent line. So remember that the equation of the tangent line, or the slope of the tangent line, is the same as the slope of the curve at a particular value of x that you're finding a tangent line. So do you guys remember from section 1.2 where we were trying to estimate the slope of a curve by drawing a line that we thought would have the slope of that curve? You guys kind of remember that? Yes? Maybe raise your hand if you recall that from section 1.2. Okay, no one remembers? One person? Okay. So maybe I should hop back to the slide, but the idea of the tangent line was that if we had something that wasn't a straight line, right, something that looks like this, we'd say, well, I don't know how fast the curve is changing at a particular point in time, so what I would do is I'd estimate it by drawing a line. So both the tangent line and the curve both share this point over here. And, well, I drew this line, so if I knew the slope of this line, I'd be happy telling you how fast the curve was changing at this point. So that's the tangent line, right? The curve is this complicated thing, but if I could just intuitively draw a line here, and it looks like it has the same rate of change as the curve, at least intuitively. So if they both share the same point over here, right, whatever point that is, they both have the same point on the curve. If I knew the slope of the line, then, I could tell you at this value of x, say x is 3, I could tell you how fast the curve was changing when x is 3 if I knew the slope of the line. So here, given a curve and a value of x, we're going to compute what the tangent line is. We can compute how fast the curve is changing because we know how to take the derivative. And we can find a point on the line because we have a value of x and we have the formula for the curve. Okay, but you guys, does this kind of make sense what we're trying to do, at least intuitively? Trying to figure out how fast the curve is changing. Okay, I got some head shakes. Okay, I'll take that as a positive sign. Okay, so for doing these, what we're going to use is the point-slope equation of the line. And remember, it's going to be y minus the y-coordinate is equal to the slope, evaluated a, which remember is the derivative, times x minus a. Right, so the point we're looking at is the point a comma f of a, right? We subtract the x value and the y value, and the slope is being determined by the derivative evaluated at that point. So this is the point-slope equation of the line from section 1.1, except we're going to calculate what the slope should be by using the derivative and the value of x that we're given. Okay. Okay, so find the equation of the tangent line to the graph of f of x equals 3x at x equals 4. Okay? Well, this is going to be a real simple one, so I'm just going to walk through what they do. So we start out with the function, which is f of x. Now, the next thing we do is we find the slope of the function, which it's a straight line, so it's just 3. You can use the power rule if you like. Subtract for the 1 from the exponent, you have x to the 0. Bring 1 in front, you're left with a 3. Okay? So now we have a formula for the function. And we have a formula for the rate of change of the function, or the derivative of the function. Notice that in this case, the derivative function is constant. It's a constant function 3. Therefore, at x equals 4, any other value, the value of the derivative will be 3. Okay, so the slope doesn't change. So now what we do is we just plug everything in. And we wind up with y equals 3x. Okay, so whenever you have a line, the tangent line will be that line. So we're going to walk through the process with something a little bit more complicated, but what's that saying is if you have your function that looks like this, okay, it's a straight line, and you want to draw a line that will tell you the slope of that line that shares a common point with it, it's going to be that same line. Okay, so what we just did is a sanity check to make sure this result makes sense. So if you have a straight line, the tangent line to that line is just the line, right? So we're going to do something a little more complicated because it's just too simple to the point where maybe it's even a little confusing. But the point here is if your function is a straight line, the tangent line is the same equation as your function, right? So my function is 3x, and it doesn't matter what point I choose, my tangent line function will also be 3x. So that's the point they're making. And the sanity check for that, just to make sure we're just not saying random stuff, is, well, if my tangent line was in blue, the function was in blue, the tangent line that I drew in red goes straight over that line, and that should kind of make sense, right? If I want to know how fast my line is changing, that's what the tangent line tells me. The tangent line should be the same line. Okay. Okay. So, find the equation. We just did that one. Okay, I want to do one more example that is going to be a little bit more involved before we go into the another notation for the derivative, which is what we're going to do next. I'm going to say, look at the function f of x is equal to, say, x cubed. We want to find the equation of the tangent line when x is equal to 1. Okay, so our function, so the first thing we're going to do is we're going to take the derivative of x, which is going to be what? 3x squared Now what we're going to do is we're going to evaluate to find the slope. We have to find out what the value of the derivative is when x equals 1. So f prime of 1 is equal to 3 times 1 squared, which is equal to 3. Now this is going to be the slope of my line, so I'm going to put an m there. M equals 3. Now what I need to do is I need to find the y-coordinate of this function when x equals 3, right? Because it has to be a slope on that curve. So what I'm going to have, I need to find f of 1 is going to be equal to, I'm using this up here, is going to be equal to 1 cubed, which is equal to 1. So now I have my slope is m equals 3, and I have my point, well, my x value is 1, and my y value, which is what I evaluate by plugging x into the original equation, is also 1. I have a slope and a point, so I can use my point-slope equation for the line. So we have y minus my y-coordinate, which is 1, is equal to my slope, which is 3, times x minus my x-coordinate, which is over here, which also happens to be 1. So that's the equation of my line. If I want to put it in slope-intercept form, I can rewrite it by saying y minus 1 is equal to 3x minus 3, and, 3x minus 3, and I can add 1 to both sides, and I have y is equal to 3x minus 2. Okay, so you can watch that again on the video too when I post it. But the basic idea is first I give him the equation, I find the formula that tells me the slope, and then I plug in the given value of x into the formula for slope to find out what the slope actually is. In this case, it's 3. Well, I also need to know the y-coordinates that I'm working with by taking the value of x and plugging into my equation over here, right? So essentially what we did was the function for f of x equals x cubed looks something like this. And what we did is we said, well, here's the point that we're looking at, x and y are both 1. And what we did is we used this line over here to draw the tangent line, which is what I drew, which is what I have circled in red, okay? The slope of this line, which is 3, is also the value of the derivative when x equals 1. And they both share the same point when x equals 1, right? They both have this point over here, and they both have the same slope at that point. Okay. So any questions so far? Yeah. Where do I get the negative 1? Well, because the y-coordinate over here is 1. When x is 1, y is 1. So the formula is y minus the y-coordinate, which is y minus 1, is equal to the slope times x minus the x-coordinate. Remember? So the formula is y minus y1 is equal to m times x minus x1. Here, y1 and x1 are both 1, and my slope is 3. And if I simplify it out, I wind up with this. No, I wasn't using y equals mx plus b. I simplified it in order to get y equals mx plus b. Okay? Say that again? Well, I can discuss that more afterwards, but if you'd like to see me after, but the most straightforward way to do it is to plug it into this formula, and if you want to find out what y equals mx plus b is, you would just simplify it to get it like this. So this is in the form y equals mx plus b down here. So we generally how do you say, use the slope-intercept form because it works so naturally with these. And if we want to find the point-slope form, we just simplify it and solve for y. Answer your question? Okay. So if we So if we continue with this, what we have here is we're going to look at the another notation for the derivative. So, and this notation has a lot of advantages. It's called the Leibniz notation. I may have said that incorrectly. But the whole concept of this derivative, it's just a different way of communicating to the reader that we're taking a derivative. So instead of writing f prime, what we write over here is we write d, and the d means we're taking the derivative. The dx on bottom is not fractions, doesn't mean division. It just communicates to the reader that the variable that we're taking, the variable in the equation we're taking the derivative of is x. And it just means the same thing as saying f prime of x. Why do we use this notation? It's part of the language, and like language, different expressions have different advantages. And this expressing the derivative in this form allows people communicating mathematical ideas to make things more clear. It has a lot of nice properties to it, is another way to say it. So an example here, if we writing the derivative, this just means the derivative of x to the 6th with respect to x. It just means we're taking the derivative of x to the 6th, using our power rule of 6x to the 5th. Again, this just means we're taking the derivative of x to the 5 over 3. Okay? And the derivative, we just use the power rule, bring the 5/3 in front, subtract 1 from the exponent. And over here, this just means we're taking the derivative of 1 over x, which is the same as the derivative of x to the -1, bring the -1 in front, subtract 1 from the exponent, we get -1 over x squared. Okay, so this notation just means taking the derivative of this function over here as opposed to writing f prime of x. Okay? Just an example of this, just to compare the two. If our function is, say, f of x equals x to the 5th, we can write f prime of x is equal to 5x to the 4th. Alternatively, we can write the derivative of x to the 5th with respect to x is equal to 5x to the 4th, right? So there's a lot of advantages to this, far beyond what I just did. But you can already see an initial advantage is I condensed 2 lines into 1 line. Now that's a minimal advantage to some of the things you can do with this notation. But just as a start off, you see if my function is f of x, f prime of x is 5x to the 4th. Right, so I needed 2 lines to express that idea. And this is just a minimal advantage of what I can do with this. There's actually a lot that can be done with this. It's a little bulkier, so we use both, depending on what's more appropriate. But this just tells me right off the bat on 1 line, I want to take the derivative of x to the 5th. X to the 5th is my function. My variable is x. Bring the 5 in front, subtract 1 from the exponent. So the notation, the properties of the notation are much more than just condensing lines, but you can already see that's at least one advantage. Okay, so that's just another different notation. Now, calculating derivatives via the difference quotient, I just want to check something real quick here. Okay. Now, calculating functions via the difference quotient, this is where the derivative comes from. Okay, most of the course we're not going to be using the difference quotient, but this is where the idea of the derivative comes from. This is where we get the power rule from. So on quizzes and tests, at least at the beginning, you will be asked to find a derivative using the difference quotient. It's to test the idea. Do you understand where the derivative is coming from, where these formulas come from? So if I say take the derivative of x cubed, I bring the 3 in front, subtract that 1 from the exponent. Well, why do I do that? It just can't come out of thin air. And it comes from a little just elbow grease of calculating slopes and figuring out a general formula for what's going on. So what we're using is basically called the difference quotient. And here's the general procedure, and then I'll talk about why we do this in a second. But we're basically evaluating the derivative at 2 points. For now, just take this slide as directions. We'll talk about why in a second, even if it doesn't make sense. But just maybe even memorize what the slide says, just for this particular moment, and then we'll talk about the why behind the slide in a second. Okay? The first thing you do is, given a value of x, you're going to do f of x plus h minus f of x divided by h. And you're going to let h get really small. We'll talk about what that means more in the next in 1.4 when we talk about limits. And then we're going to after we let h go to 0, 3 is the derivative. 3 is what the answer is, and we're calling that f prime of x. So for now, just even copy this procedure down, get it to memory, and we'll talk about what we're doing with it. Okay? Sometimes in math, you see a definition for something, like even myself, I read it, I have no clue what it means until I start looking at some examples to get an idea of what it's saying. Okay? So let's look at this. Before we look at this slide, let's take a look at what it's saying. Let me do an Alt tab over here to go to the document. So what are we saying here? So we have, if we have a function, and say the function looks like this, okay? And it's maybe like x squared or something. This could be like f of x equals x squared. All right. And we want to know what the slope of the line, the slope of the curve at this point is, or the slope of the tangent line. They're the same thing. So say this is my point, and say this is the point 1, 1 if you like. Well, the problem is, if I want to find the slope of this, and the tangent line is going to look something like this, right? And it's one thing to draw it, but how do I compute it? So the general idea is, what we're going to do is we're going to take this point, which is going to be our x value, so in this case x is 1, and we're going to take another point, which is x plus h, or in this case would be 1 plus h. And that's this point over here. Okay? All right? And what we're going to do is not draw the tangent line, but what's called the secant line, or it's just the line between 2 points on a curve. So what we're going to do is we're going to connect these 2 points. Okay? And we find the slope of this line. Now the slope of this line is an approximation to the tangent line, the slope of the tangent line. It's a bad approximation because x is this other point. This is 1, this is 1 plus h, whatever h happens to be. Could be 2, 3, 5, a half, a fourth. But the smaller h is, or the closer these 2 points are, the better the approximation is, right? So the slope of this line is an approximation to the slope of the tangent line that we want. Well, how do we get a better approximation? Well, if I have another marker, which I do somewhere. Yes, I do. And fortunately, it's a black marker. What we're going to do here is we take, instead of using this point, we're going to go a little bit closer and make x plus h over here. And we look at, say, this point. And I'm just connecting these 2 points now. And as you can kind of see, the line I drew is starting to mush into the curve a little bit, which is what I like because it's getting closer to what the curve is doing. And as h gets smaller and smaller and smaller, these 2 points are getting closer, and the result is the tangent line. So I don't know if that was clear or not, but basically the idea is if I start with something like the curve x squared, I pick a value of x, say x is 1, and I pick another point out here, I connect them, I find the slope of that line. Then what I do is I pick a closer point on the curve. As h goes to 0, these 2 points are getting closer. So this is my x plus h. Then if I make h smaller, it means I'm picking a closer point on the curve. Say here's my x plus h. I connect those 2 points with a straight line. I find the slope of that. That's the slope of my tangent line. That's the derivative. If as h goes to 0, I eventually wind up with this line over here. That's the tangent line. So the basic idea is to pick 2 points on the curve, calculate a line through those 2 points, find the slope of that line, that's the derivative. Now, letting h go to 0, I find an equation, and use an arbitrary value of x, I can find an equation for the tangent line. Okay? Which is the derivative. Okay, so let's do an example. I'm going to do a slightly simpler example than the one they're using, then I'll go through their slide. I'm going to compute the derivative of the function f of x equals x squared when x equals negative 1. Okay? So just to review the process I'm going to use, let me go back a slide. First thing I'm going to do is set up the difference quotient. Make sure you have these steps memorized. I'm going to go through an example. Then we're going to let h get really small. And then the result is going to be the answer. Okay? Sometimes they cover this in algebra courses, in pre-calc courses. Sometimes they don't. So maybe you've seen this before, maybe you haven't. How many people have seen this before? How many people have not seen it before? How many people are not sure? You think it's not ready? Okay. All right. So when I took algebra, I didn't get taught this. First time I saw this, I was either calculus or pre-calculus. It depends on the textbook and what they do. So if you haven't seen it, I think they're introducing it in algebra courses more and more, just to help get students ready for calc. But let's do an example. We all know how to take the derivative of f of x equals x to the 5th. So we all know how to take the derivative of this function. X squared, I'm sorry. Let's do x squared. We all know how to take the derivative of that function. What is it? 2x. Let's use what's usually the three-step method, which generally referred to as the definition of the derivative, right, to calculate what it is. So what we're going to do is the first step says we're going to look at step 1, and we're going to calculate the derivative when x equals 1. So the formula is going to be f of x plus h minus f of x divided by h. Right? Well, first I'm going to do, well, x equals 1, so f of x plus h is just going to be f of 1 plus h, right? Because x is 1 and I'm adding h to it, right? So instead of x plus h, I have 1 plus h because x is 1. Well, this is going to be, whatever value is in here, I'm going to substitute in for x, so this is going to be 1 plus h squared. F of x is equal to x squared, so f of 1 plus h is equal to 1 plus h squared, right? So this says square whatever x is. Well, x is 1, whatever value is in parentheses here, square it. Well, the value in parentheses is 1 plus h, so I'm squaring the whole thing, right? F of x is a function is basically a set of directions. What the directions are doing is whatever's in parentheses, square it. Here, what's in parentheses, 1 plus h, I'm squaring it. So what does this give me? Well, I can FOIL it. I'm not going to review that right now, but if you have questions, ask me. If I FOIL this, I get 1 plus 2h plus h squared. Okay? The next term I need is f of x. Well, f of x, well, x is 1, so this is just f of 1. Well, f of 1 is just 1 squared, because the directions say square whatever's in parentheses. What's in parentheses? 1, so I square the 1, and I just get 1. So let's rewrite the above. F of x plus h is given by 1 plus 2h plus h squared. And that's my f of x plus h, and I'm going to minus 1 because that's my f of x. So f of x plus h is this term over here, f of x is this term over here, and I divide the whole thing by h. Okay? And the parentheses aren't doing anything here. So I can just remove the parentheses. I'm not distributing anything across. I mean, there's nothing in front of the parentheses, so I can just remove them. So this is just going to be 1 plus 2h plus h squared minus 1 divided by h. The 1's cancel. Right? And I wind up with 2h plus h squared divided by h. And now what I'm going to do is I'm going to factor out the h. So these guys are equal. I just canceled the 1. So this is going to be equal to h times 2 plus h. Divided by h. The h's are going to cancel, and this is equal to 2 plus h. Okay, so the most difficult thing I did here is the algebra. It's going to take a little practice to get used to that. But just to lead you through the steps I just did again. First step, find f of x plus h. Excuse me. The first thing we're doing is we're finding f of x plus h minus f of x divided by h. Well, x is 1, so we want to find f of 1 plus h. Well, the directions say whatever is in parentheses square it, so we're going to square 1 plus h to get this. The next term is f of x. Well, x happens to be 1. So we want to find f of 1, and the directions are to square whatever in parentheses. Well, we have a 1, so we're going to square it and get 1. And then this, well, f of x plus h is this term. F of x is this term, and we're dividing by h. So now what we want to do is we want to simplify it. Well, the parentheses don't matter is what I do on the next slide, so we're just going to do 1 minus 1. We're going to cancel those. Since there's nothing in front of the parentheses here, there's not a negative sign, there's not a 5 or anything, we can just remove them. And we cancel the 1's, and when we cancel the 1's, we wind up with 2h plus h squared over h. We can factor out an h using the distributive property, and we cancel the h's to get 2 plus h. Because h divided by h is just 1, so they cancel out, wind up with 2 plus h. So we wind up with f of 1 plus h minus f of 1 divided by h is equal to 2 plus h. So that's step 2. Step 2 now is to let h go to 0. What happens in this expression over here as I let h go to 0? What's happening? Can someone tell me if what happens if h equals 0? What is 2 plus h if h equals 0? 2, right? So as h goes to 0, this expression here is getting closer to 2. And we're going to say f prime of 1 is equal to 2. The derivative of the curve at that point is 2. So you're going to get some practice with this on the homework. You run into questions, a good place, as you're working through these, come to my office hours, go to the lab, go to the tutoring sessions online. So work through them. They take some practice, but the general idea is we know what f of x is, so we can compute this over here. And we can just plug everything into the formulas as we did, and just algebraically simplify it. And we wind up with the derivative of 1 is 2. So, again, where does this idea come from? Well, if my curve is something like this, before I do that, we just maybe want to check. We want to maybe check that this is correct. Well, I'm going to do that up here so I don't waste some paper. Well, f of x is equal to x squared. F prime of x is equal to 2x. So f prime of 1 is equal to 2 times 1 equals 2. So using the definition of the derivative, we get f prime of 1 is equal to 2. Using the power rule, which comes from the definition, f prime of 1 also equals 2. So they agree. Where does this idea come from before we move on to the next slide? Well, if this is my curve x squared, and say this is x, and this is x plus h, then the slope, or the derivative, the slope, if we just take the slope between these 2 points on the curve, we just take the slope of the line between these 2 curves, we know that f prime of x is just the slope of those 2 points, is going to be the difference of the y values, which is this one y value is f of x plus h. The other y value is going to be f of x. And it's going to be divided by f of x plus h minus x, which just becomes, I don't want to put an equal sign here because that's the derivative. This is just that secant line. But the slope of this line over here, it just becomes the x's cancel, and we wind up with f of x plus h minus f of x. The x's cancel, so we just wind up with an h on the bottom. So that's where it comes from. It means taking the x value that you fix, that you want to know the slope of the curve at that point, pick another h, another value on the x line that's 8 units away from this, that's h units away from this value. So you have 2 x values, x and x plus h. The difference in the y values, which is given by f of x plus h and f of x, divided by the difference of the x values, x plus h minus x, which is just h, gives you the slope of this red line over here. And as h goes to 0, you get closer and closer to this line. So I know that may come across as a little bit of a fuzzy subject, but maybe intuitively just what you're doing is you want to know the value at this point, so you just pick another point and let h go to 0. So as this point gets closer to this point, the slope of this red line over here becomes closer to this red line over here. Okay. So any questions on it? I'm sure there's questions, but anything immediate? Any immediate questions? Okay. Okay. So let's look at one of their examples. What they're doing is they're, well, I'm going to skip their example because I want to give you guys a chance to digest what you just saw. Maybe move on to something else. Maybe I'll do this example next time. But essentially, but before I do that, maybe just write this one down and see if you can do it by yourself at home. Maybe just try it. You have the steps written down. See if you can go through at home. And when I go through this one next time in class, like see if you can do this before Wednesday. I know you got other homework you're working on, but just if you have a few minutes, just try to work this one out before Wednesday. And I'm going to go through this example in class. And you know, if you want to go to the tutoring hours and ask for something, feel free to do that. If you have any questions, but try to work this one out before next time in class. Okay. Minus x squared plus 2. All right, so let's see, got 8 minutes. And okay. So I think we'll get through the end of the section. There's only a couple things left, if not next time. So not all functions are differentiable. In fact, in finance, you come up with a lot of functions that are not differentiable because, say you're trying to look at like a stock market. You're trying to fit a curve to something, right? It's very jagged. And so they work with something called stochastic calculus there because those functions are nowhere differentiable. Here we're just going to look at an example of something that's not differentiable at one point. The example we're going to use is the absolute value curve. The problem with the absolute value curve is it's not differentiable at 0 because on the right-hand side you have a straight line. Everywhere on this straight line the slope is 1. On the left-hand side of the 0 you have another straight line. The slope of this straight line is going down, so it's actually negative 1. So what should the slope at 0 be? Well, 0 is a point on this line, so it should be negative 1. But it's also a slope on this line, so it should be positive 1. Well, what should it be? Well, we're not sure. Okay? So it's not differentiable. If any of you guys go into like mathematical finance or something, then you'll start addressing those types of questions, right? What is as to what it should be, because you wind up with really, really jagged looking functions. Like look at a stock market graph, very sharp, it's very jagged in a lot of places. So this is not just a one place phenomena, it happens everywhere. Okay? So not all functions are differentiable, and an example of that is the absolute value of x, which is this function that looks like this. And the reason is you have two straight lines kind of pasted together, and where they intersect, you're not sure what value 0 should have here. Okay? Okay. So this is just another example of what we did before. If we use this definition over here and let h go to 0, then that gives us the derivative. Okay? Again, I might do that example or some others next time. So if you want another example, I'll work this one out next time, but if you want another example to go through, here's another example you might want to try. If you want to write this one down, just give this a try. I'm going to go through this example next lecture. I want to give you guys a chance to digest it. But negative x squared plus 0.05x minus 2. Try to do this one and the other one I mentioned before Wednesday if you have time. Focus on the homework, of course. Go into office hours to get through with that if you need to. But if you have time, look at these. And that's the end of section 1.3. I don't have time to start 1.4. So, good luck, and I'll see you guys on Wednesday.